Hi there and welcome to our next lesson in our C3 topic, chemical economics, and today we're going to be looking at carbon and chemistry of carbon atoms and the different forms that they have, which are known as allotropes. Anyway, I will see you at the end of the lesson. Bye bye. Okay, so let's have a look at our objectives for today's lesson. So by the end of this lesson on allotropes, you should know and understand the different arrangements of carbon in diamond, graphite and Buckminster fullerene. Now a carbon atom looks like this on the periodic table. So we have a relative atomic mass of 12 and an atomic number of 6. Now carbon is a really important molecule or atom, and we're going to have a look at some of the molecules that exist with carbon. Now the different arrangements of carbon atoms are what we call an allotrope, and that is the different form of the same element. Now with the allotropes of carbon, they have a different arrangement of atoms. Now there are 3 arrangements: carbon graphite, carbon diamond and a Buckminster fullerene. Carbon graphite is quite a common form of carbon. It's the form of carbon that you find in your pencil lead. Now here you've got your black dots which represent the carbon atoms. Now these are in a hexagon arrangement and the hexagons are joined together, so you might be able to see this clearly here where you have the blue and white dots which are the carbon atoms, and then the sticks between them are the covalent bonds. Now the covalent bonds are very strong, and you can see in here that each carbon atom is covalently bonded to 3 other atoms within that hexagon. Now once you've got your layer of hexagons, which is relatively flat here, you then have a second layer underneath. Now the second layer is held together by a very weak intermolecular force. Now the weak intermolecular force keeps the layers together, however the layers can slide apart. Now the layers being able to slide apart makes it useful for when you're writing with a pencil, that some of the layers are pushed and move and are able to become separated, which leaves the drawing that you've done in pencil on the paper. Now the weak intermolecular forces are caused by delocalized electrons. Now those delocalized electrons means that they are electrons that are not held by any particular carbon atom. So this means that carbon graphite is extremely useful as it can conduct electricity. It also means, because of the strong covalent bonds, it has a very high melting point. Now the high melting point, the ability to conduct electricity, means that carbon graphite is extremely useful as an electrode. Now carbon graphite is also insoluble in water. It is also lustrous and opaque, meaning that light cannot travel through it. It also has a dark colour, which makes it useful for pencil leads. Now one of the uses for graphite is as a lubricant, and it's because of the layers and the ability for those layers to move and slide across each other. Now because of that, the use of the pencil that we mentioned earlier, and it can be used as a lubricant because it allows bits that are attached to the graphite to move as well, which means that carbon graphite can be very slippery. Now the second structure of carbon that we're going to look at is carbon diamond. Now like carbon graphite, carbon diamond can be made of millions and millions of carbon atoms. Now they're held together like the graphite with a strong covalent bond. Now like the carbon graphite, this strong covalent bond means it has a very high melting point. Now unlike the carbon graphite, each carbon atom here is bonded to 1, 2, 3, 4 other carbon atoms. So whereas the graphite had 3, carbon diamond has 4. Now each of the electrons within the carbon atom is held within one of these covalent bonds. This means that carbon diamond has no free electrons, so therefore cannot conduct electricity. Now because there's no layers, these along with the covalent bond mean that carbon is very, very hard, and in fact carbon diamond is often used on drill tips because it's able to break up rock very, very easily without damaging itself. Now, like carbon graphite, carbon diamond is insoluble in water. It also has no colour, so it's colourless, it's clear, and it's lustrous and shiny. Now, some of these properties mean that it's very useful for jewellery. Now, with jewellery, if somebody gives you a diamond ring, one of the ways that you can test it is it will be able to smash glass because of these strong covalent bonds and the fact that it's very, very hard. So if somebody does give you a diamond ring, one of the ways you can test it is by trying to crack or scratch glass. If it's not diamond, it will just shatter itself. Buckminster fullerene is a relatively recent discovery of one of the structures or allotropes of carbon. Now, unlike the graphite and the diamond, Buckminster fullerene has a limited number of carbon atoms. There are only 60 carbon atoms within a Buckminster fullerene structure. Now, Buckminster fullerene is made up of carbon atoms in hexagon shapes and in pentagons. So you can see here 1, 2, 3, 4, 5, 6 sides, and then here 1, 2, 3, 4, 5. Now each carbon atom is covalently bonded to 3 other carbon atoms. So similar to the graphite, each carbon is covalently bonded to 3 other atoms. Now Buckminster fullerene is insoluble in water, however it is soluble in petrol. Now the structure of Buckminster fullerene is very useful, and it is used in a lot of industrial processes known as nanochemistry and nanotubes, and we'll be focusing on those in next lesson. Okay, so that concludes our lesson on allotropes and allotropes of carbon. So let's summarise what we have looked at today. We have looked at the 3 different allotropes, so we've got carbon graphite, carbon diamond and Buckminster fullerene. The similarities between them is they have the covalent bonds between the carbon atoms. The graphite and the Buckminster fullerene, which have the 3 bonds to the 3 carbon atoms, and carbon diamond has the 4 bonds. We've looked at the properties and the reasons why they have those properties due to their chemical structure. Anyway, I hope you've enjoyed this, and I will see you next time. Bye bye.